Hello and welcome. Let's talk a little bit more about basis sets. We've already mentioned that the larger the value of the numbers, the more digits you see, the more symbols you see, the bigger the basis set. And the idea behind the Pople-type basis sets is that we're trying to replicate hydrogen-like functions with series of Gaussian functions. Now, STO 2G, 3G, 6G, we'll see this on a different slide. This is like, we're going to take every Gaussian orbital for each atom and just try to replace it, not for each atom, for each orbital of each atom, and replace it with a series of Gaussian functions. Pople said, well, let's split the valence. Let's actually split the outer valence into a couple chunks instead of just having one piece, if you will. And one way that we can see this, if you look at, say, like a 321G, a 321G is going to give three functions for the inner core orbitals. Picture a carbon atom. Carbon, you're thinking like a 1s2, 2p, 2, I missed the 2s, 2s2. So 1s2, 2s2, 2p2. So you're thinking, okay, I'm imagining a 1s orbital for carbon. It's one of its core orbitals. We're going to replicate that 1s orbital, which should just be one function, but with three Gaussian functions because of this 3 here. And then for the outer core orbitals, which are the 2s and the 2p orbitals, 2px, 2py, and if you want to include all orbitals, the 2pz as well, we're going to take, for each one of those orbitals, we're going to take 2 plus 1 functions and try to add them together to replicate it. And the idea of the 2 plus 1 is we can have two functions that are kind of centered around maybe closer to the nucleus, and then we can have a third that maybe is going to be centered somewhere else. That's going to allow more functional form for these now larger valence orbitals. So the issue here is, do we want three orbitals centered around the same location of space? Or do we want two like closer to the nucleus, one further away? Or do we want to use one of these bigger type basis sets where we have, like 6 for the core and then a 3-1 split or a 3-1-1 split? We really have a lot of choices here. But the key is that each split is just adding, like if you look at the 3-1-1, the extra 1 here is just going to add like another split even bigger. So it adds more functional form for the orbitals to be replicated with these Gaussian-like functions. Okay, then polarization, we mentioned this before. We can add d orbital polarizations with the star symbol. It keeps flashing. I don't know why it's doing that. It seems to be done flashing. So we can add polarization with the star symbol or 2 stars and even more. So we can add polarization such as d. So if we see a 631G d, that's the same as the star. That's adding depolarization to p orbitals. So it's taking every p orbital and polarizing it with d orbitals, making these looking orbitals here. Really helpful for trying to describe, adding polarization functions is really important for trying to describe tetrahedral molecules. Likewise, you can polarize an s orbital with p orbitals, or with p functions, with the star-star basis set, or the dp basis set. So the key is noticing that the star and the d mean the same thing, and then the star-star and the dp also mean the same thing. And then you can also add multiple layers. You can add like two sets of d functions instead of and f functions as well. You can add 2 sets of p functions. You can really go crazy and add lots of polarization. You can then add diffuse function. This adds a larger split valence shell, but just to heavy atoms. So if you're doing a calculation on CH4, you might say, is there some way I can add an extra function onto the carbon atom, but not necessarily the H atoms? And the answer is you can do that with a plus symbol. So what a plus symbol does is it's kind of like doing a 6-3-1-1, but on the carbon atom in that calculation, but just a 6-3-1 on the H atom. And we'll go through some examples of how you might add up the number of functions after a couple more slides. Now let's take a look at what it means here, like what we're trying to do. So the first slide here is looking at the nominal Slater type orbitals. So these are kind of like the functional forms that we're trying to replicate here. So we have our 1s orbital, our carbon 1s. Let's see here. This is the carbon 1s, hydrogen 1s, carbon 2s 2p orbital. What this slide here is looking at is a Slater-type orbital versus the Gaussian function. So Slater-type orbital is slightly more what we're trying to mimic here with our Gaussian function. You can see one Gaussian function isn't really replicating that blue curve very well. Now, we can do a better job if we take, instead of just one Gaussian function, what if we take 3 or 6? And you can see we're getting better agreement if we use 3 Gaussians to try to mimic that function, or 6 Gaussians. So like an STO3G is trying to take 3 Gaussian functions to replicate that Slater-type orbital. Sort of the idea. And the Slater-type orbital is like the mimic for the it's like sort of the idea of the hydrogen-like orbital that we're trying to replicate. Okay, so STO3G, STO6G, if we're doing this on like CH4, what this would mean for CH4, you would say for each orbital in the calculation. So the minimal orbitals I need are for carbon 1s, 2s, 2p, x, y, and z, the full 2p set. And then for each hydrogen, I need 4 1s orbitals. So I need 1, 2, 3, 4, 5 for carbon. And then I need 4 orbitals for hydrogen. So I need 9 orbitals. And I'm going to replace each of those orbitals. Let's say we're doing an STO6G. I'm going to use 6 Gaussian functions per orbital. I need 54 Gaussian functions. Now you can compare that and say, well, in terms of basis functions, STO3G would be half the size. Now remember, cutting a basis set in half saves you way more than half the time because of the scaling over calculation. So the issue here is you can kind of get a sense for how a change in basis set can increase the size of a calculation and how that increase in size might correlate to an increase in time for your calculation to take. Now, let's get on to a discussion of the, or come back to the discussion of, our Slater-type orbitals versus the Pople-type basis sets. So instead of an STO2G, 3G, 6G we mentioned before, well, instead of doing like a 3G for everything, why don't we do like a 3 centered around one point and then a 2 plus a 1 with a better functional form. So now if we compare, like let's look at a 631G basis set for CH4 and how this might compare. So for CH4, I still need my like 9 orbitals. I still need my carbon. I still need my 1s, my 2p, my 2s, my 2p, x, y, z orbitals. And then for hydrogen, I still just need the 1s. And so then for carbon, with the 631G basis set, it's like what I need, and I could track this separately in terms of the number of basis functions I need. So I need one basis function for the 1s orbital, and it needs to have 6 Gaussian functions to mimic that Slater-type orbital. And then the 2s is going to get, instead of one basis function, it's going to have 2 basis functions that have the sum of the 3 and the 1 for the 4. So the fact that there's 2 digits here mean that I need 2 basis functions for each one of my valence orbitals. And let's just actually just do it like this, that this is going to be multiplied by 4. Multiplied by 4 for each of the 4 valence orbitals. So 2 basis functions, 4 Gaussian functions. And then for hydrogen, the 1s is its outer core orbital, so the 3 and the 1 apply. So it's a 2 and a 4. For CH4, we need to account for the fact that we have 4 atoms. So I'm multiplying the 2 and the 4 for carbon by 4 because I have 4 orbitals, 4 valence orbitals. And then for hydrogen, I'm multiplying by 4 because I have 4 H atoms, if I'm assuming I'm doing a calculation on methane. And I could add these all up, and for comparison's sake, why don't we do that? So in terms of the basis function count for carbon, I'm going to have 9, and then I'm going to have 14 plus 6, 16 plus 6, I mean. So that'll be 22 Gaussian functions, and then we're going to have 8 and 16 for our basis functions and our Gaussian functions for the H atoms. And so in terms of the total here, this would be 17 basis functions, and it would be 38 It's always the hardest to count when you got a video recording, but so that'll be 38 Gaussian functions. So interestingly, if you compare this to the like STO6G, fewer Gaussian functions, but they're like somewhat being better placed in the molecule where you need that greater functional form and then saved in areas where maybe you don't need that functional form. It's also more basis functions. So for calculations, it's likely that we're going to need more basis functions, and then we're going to need to find a way to to best spread those Gaussian functions around. So here for 631G basis set for CH4, 17 basis functions, 38 Gaussian functions. So our polarization, the polarization is going to add d orbitals with the star symbol, d and p orbitals with the dp, even more. We're just going to consider the size of the dp or the d here. So what we're adding with the d functions is we're adding 5 basis functions and 5 Gaussian functions. Oddly, some basis sets will actually add 6. I really don't want to talk about why. It has to do with spherical versus canonical space and how the basis set is constructed, but we'll just leave it at that. The p functions, regardless of the basis set, are going to add 3 Gaussian functions and 3 basis functions, 3 Gaussian functions. So minimally, each of the p orbitals, we get a basis function. Each of the p orbitals, we get a Gaussian function. Then our diffuse function is going to add that larger split onto the valence shell of each of the valence orbitals. So a plus symbol is going to add 4 basis functions, 4 Gaussian functions. This is if you're picturing something like a carbon atom, which should have 4 valence orbitals. So you're adding 1 basis function, 1 Gaussian function per valence orbital. And then the plus plus is going to add the same for your heavy atoms, but then it's also going to add 1 basis function, 1 Gaussian function for your H atom. So plus sign, 4 basis functions, 4 Gaussian functions for second row plus elements. And we'll see some examples. We'll go through those, I believe, in the next slide. Okay, here's a blank slide for us to compare. Let's go through. I just kind of wonder if you hear my dog snoring in the background. I hope you do. Otherwise, it's a weird intro. So let's look at CH4. Let's use the 6-31 plus G dp. Let's do this basis set. The way I like to break it down is, okay, compare hydrogen versus, carbon versus hydrogen. Go through the orbitals you need. I need, for carbon, a different set of bases. I need a 1s, and then 2s, 2p. Let's do it separately. 2px, 2py, 2pz. So for carbon, I'm going to need 1 basis function of 6 Gaussian functions. And then it's going to be 2 and 4 for the valence shell. Plus symbol is going to add 1 basis function, 1 Gaussian function per valence orbital, of which there are 4. So the plus sign's adding 4 and 4. And then the D adds something for P. The D is adding polarization functions for things like carbon. The P doesn't really do anything for carbon. So the P doesn't do anything for carbon. That's going to be for hydrogen. So the D is adding 5 basis functions, 5 Gaussian functions, 1 for each of the d orbitals. Like I said, some actually add 6 and 6, but we're not going to worry too much about the distinction. And we can add these up. I'm not going to be too concerned about adding those up. Hydrogen. The other thing I would say is if you were considering like C2H6 instead, you would be like doubling the count for carbon. If you're doing C3H8, you'd be tripling the count for carbon. So the total number of basis functions that you need for your calculation depend on how many atoms there are in your calculation. So if you're doing a calculation on like C6, H12, O6, obviously we're going to need more functions simply because we have more atoms. Okay, for H, we have a 1s, the plus, and then we can think if the plus means anything, and the P are going to mean something for hydrogen. So the 1s, this is a valence orbital, so that's why it's a 2 and a 4, not a 1 and a 6. So 2 basis functions, 4 Gaussian functions, and then the plus is not doing anything for hydrogen. If we had a double plus, then we'd be adding a 1 and a 1. But a double plus, like a 631 plus plus basis set, is really just a 6311. So if you kind of think about it, the double plus is a weird basis set because it really is just some other basis set. So like a 631 plus plus G would just be the same in terms of the Gaussian functions that we'd be specifying as a 6311. Because what we're essentially doing with the plus symbol is a 6311, but just on the carbon atom, but not on the H. So the whole point of the diffuse function is have some way of adding an extra function to the bigger atom, but not necessarily onto the smaller atom. So you can save some computational time with the 631 plus G basis set by not adding this function. So you save the function, but also save it off of 4 atoms in your calculation. P polarization adds 3, 1 for each of the p orbitals. And so we'd, for hydrogen, it's easy to add up. I'll do this. 5 and 7 here for the basis function, Gaussian function count. And then we're multiplying this by 4 for each of the H atoms. Okay. And so that's a basic example of a Pople-type basis set. Now, we mentioned these basis set extrapolation methods. Now, a basis set extrapolation is going to need a more sophisticated might be a word, but a more clear way of increasing the size in a regular pattern. And that's going to be accomplished through a different type of basis set called the Dunning-type basis set. And so the Dunning-type basis set are these ones here, like the take this functional form, like the quadruple zeta, the quintuple zeta, the sextuple zeta. So like if you notice here, the like dtqz. So like these are all increasing in some regular pattern. Let's take a look at these basis sets in a little more detail. So the Dunning-type basis set are more correlational consistent. So these are better used for basis set extrapolations. The PV-DZ stands for the polarized valence double zeta basis set. Triple zeta is the polarized valence triple zeta. So you got the DZ, double zeta, triple zeta, quadruple zeta. And then from there, we'll just go quintuple or 5Zs, 6Z, 7Z. Obviously, those are going to be quite large basis sets. The double zeta, what it does for hydrogen and helium, what it does, it adds 2 sets of s orbitals and a set of p functions. So 2 sets of s functions and 1 set of p functions for 5 total functions. For hydrogen and helium, if an atom's in the second row of the periodic table, we'd get 1 set of D, 2 sets of P's, and then 3 sets of S. And so you're just looking at 1, 3, and 5 here. So you're doing 5, and then 2 times 3, and then 3 times 1. And so that'll be 3 plus 6 plus 5, which is 14. Just did the math in my head to make sure. And so then likewise, if you're using the double zeta basis set and then an atom in your calculations in the third row of the periodic table, then it's getting 4 sets of S functions, 3 sets of P functions, and 1 set of D functions. And that should give it 4 times 1 plus 3 times 3 plus 5. And so that should be 4 plus 9, which is 13, plus 5 is 18 functions. Okay, so if you're doing a calculation on CH4, with a double zeta basis set, you're looking at H, 5 functions, times 4 is 20, and then carbon's getting 14. So you have a total of 34. And these are the more like the basis functions and the Gaussian functions. And the Gaussian function count, never quite known what that is, and it's not something I'd be concerned about for comparing Dunning-type basis sets. Now, if you want to compare a triple zeta basis set, the triple zeta, what it does is it like adds an S, adds a P, and then adds in the D functions. Okay, and so what it's going to do, it's going to increase the 3 plus 10 plus 5, or excuse me, 3 plus 6 plus 5 for 14 functions. And then the same thing, the triple zeta for the second row adds another set of S and P and D, and then adds in the F functions. So it's like you're adding in a very clear set of additional functions in a regular pattern. So for CH4, basis set's going to be a tremendous number of functions just to go to the next bigger basis set. So the next bigger basis set in this type would be 30 functions for the second row. So if we're looking at a calculation on CH4, the carbon would need 30 functions, and then we'd have 4 times 14 for the H atoms. Quadruple zeta is going to get really big really quick. Now it's going to be 30 plus 30 times 4 plus 55. So you can see the Dunning type basis sets and how they compare. Now, if we want to do one more example of the Dunning type basis set, let's do a calculation on C2H6 with, say, the triple zeta, the PBTZ basis set. So here we'd have 2 times 30 for the carbon, and then plus 6 times 14 for the H. Don't need to memorize these, just look at the chart to figure these out. Okay, that's all. Thanks for your attention.